Okay, shall we continue? Okay, now let's consider this problem in which you want to track the vehicle using a LiDAR. For example, LiDAR, you want to track. Okay. So can we use what we studied? What we studied is what we studied so far. What we studied is nearest neighbor CMK. Okay. Now we are going to see whether we can use that for this particular problem. Before I talk about that, I would say there's a point target versus extended target. Can anybody show the difference between these two? What's the difference? Point target will be single detection. Point target is single detection and extended means multiple. Depend on what? Which decide whether it's a point target or extended target? Sensor or target? Target size. And sensor. Yeah. So this is decided whether it's a point or extended divided by combination of target and sensor. Okay. For example, a car could be a point target for an airborne target, airborne radar track. But that's an extended target for tracking from another car. Okay. So extended means you will get more than one detection from a car. Point means only one detection from a car. So in this course, we study only about this point target, and that's what I do most of my life. I work on the point target problem. Okay. Now you want to use it. So this red tracks are produced by tracker, which has seen point target tracking problem. So somehow I converted this into a point target tracking problem and used my algorithm. So how do we convert this extended target tracking problem into a point target tracking problem? That's the first task you have to do. Then you apply. Okay, how do we do? That's the thing. Because I am not going to talk about nearest neighbor CMK, okay, right? So now we are going to see this is given. How do you formulate it such that we can use that part?
Still, I don't. It's like DB scan.
Cluster.
Cluster.
Yes, that's the first step. You want to do cluster, right?
The extent information about the data.
Yeah, so clustering is what we are going to do is if you have a region like that, so we don't know how to handle this with task. So what we do is first we do the clustering. When we cluster that, we assume this is one cluster, this is another cluster, this is another cluster. Are you okay with that? So we have three clusters. Then what do we do after clustering? Okay, let's find the center of that. Okay, so now we say that this is center, this is the center, this is center. Then what? Then track the center. Correct? So then we are going to track the center. Then this becomes a point target tracking problem. Okay. But there are challenges with it. So you can simply say that I would do that and that it works, right? Now let's consider a car. Say this is your car. This is our platform. A car is here. Okay, that's a target. What kind of detection do you expect? Do you expect a detection like this, or do you expect a detection like this? This is one, this is two. Which one do you expect? Only one, not two, right? Because only one side is visible from there. So if you find the center, you would see only this. Is that right? And next time, in the next frame, say, assume this vehicle moves here. What would you get? The detections will come from like this, this, and this. Are you okay with that? Two sides are visible. Now, if you find a center, where would you have it? Center might somewhere here. Is that right? So that is a problem. If you are tracking the center of the car, that's a different problem. Okay, but you what? Okay, say let's say you want to track the center of the vehicle. Okay, that's what you want to track. But the measurement, okay, the center is moving like that. This is a some reason I can't go in it. Yes, I can. Singles. Let me restart. I don't know. Okay, while it restarts, so we can discuss about that problem, right? What I mean that the center of the car is different from center of the cluster. Do you understand that part? Because the visible sides are different. Because of that, center of the detection has some bias respect to the sensor of the car. So how do we handle that? Because that is a problem, right? Because like it fluctuates, right? How do we handle that? Pardon?
Minimum distance
Could you repeat that? Could you expand it?
in the all available detection.
Mm-hmm.
In all available detection. Very private and minimum distance.
Yeah. So okay. So instead of tracking the center, I prefer to track the closest corner. If you think that, because we can decide which one you want to track, right? If you track the center, in my opinion, it's not a problem because center is fluctuating. If you want to do that, you have to have a larger measurement covariance for the center itself, right? So if you do that, but instead of tracking a center, another option is tracking the closest corner of the other vehicle. That will not fluctuate a lot because that's always visible to us, right? So then now question is, you know how to find the center because you find the cluster, you find the center. How do you find the closest corner? Pardon? Nearest point. Yes, you can go with the nearest point. Because the problem looks simpler, but if you go into the, even now, I'm not happy with the tracker I have with the extended architecture problem because it has several problems. Okay. And the reason is that, I hope I can write it. Okay, it works now. Okay. Earlier, what I was saying that if the target is moving like this, center is here, but the observed center could be biased like this, here, and here. So if you want to handle that situation, for the when you estimate a cluster point, you have to give the covariance of R, right? So you may need to use a little larger covariance to factor this fluctuation bias. That's one way to do. And the other one, what I said is, if you are getting the closest corner like this, we can get the closest point and then track that from that cluster. That is fine, right? For that, one of the answers that we had was that we can always go with the nearest point on that will work. That is reasonably okay, but challenge at somewhere. Sometimes the challenge is like this. sometimes you will get a detection like this. You won't have detection exactly on those phone. Okay. In this case, then you will pick this so that as the phone. Again, that will introduce some problem. For that, usually what I do is, after doing clustering, we will do L fitting. You can call L fitting or rectangular fitting, in which you fit this with the rectangular form. That itself is a harder problem. Okay, that's not an easy problem. Sometimes there are multiple rectangles set up as people for that. Okay. So first we will do this rectangular fitting. If you do the rectangular fitting, then that's okay. You get the closest of that rectangular point. Okay. But the rectangular fitting itself is little harder. But you can, once you find it, you get the corner and you track it. So what in this case, what is your state? The challenge with the closest corner is one of this. Let's say your car is parked. Okay, your vehicle is parked. The car and the other first it goes here. Other car goes here. Then it goes here. Then it goes here. Okay. So in the first case, which one is the closest corner? In this case, which one is the closest corner? This one. So you say you want to detect this. You are tracking this. When it comes here, which one is the closest corner? This is the closest corner. Then this is the closest corner. So this becomes a problem. You see that if you track this as a closest corner, then your prediction will say somewhere here, this will not fall inside the gate. So if you use a nearest neighbor, that will not fall inside the gate of the predicted one. So because of that, the closest corner solve one problem, but introduce another problem. You see that? How do you handle this? You want to do the normal nearest neighbor tracking, you have to track the same point in the object. You can't, that point cannot jump. If you jump, that's going to be a problem. Yes, that's right? So what you have to do is, you have to have a way to identify a switch in the nearest point. Okay? That means this one predicting over here, then you identify that switch, then your prediction has to come here. Alright? You identify the switch, you predict, identify the switch, then bring it here, then that. So what do you need in order to bring that over here? In order to bring this one over here, what information that you need to have? Length of the vehicle. How do you know that? How do you know the length of the vehicle, right? We don't know the length of the vehicle. So that change the problem. So we due to that, now the problem becomes x dot y dot of the corner. You want to find length, width, and theta. Do you understand that? So we want to estimate everything. Then only you can go from here to here by using this length or width, whatever you want. Right? So, but still it's a point target tracking problem. This is a point target tracking problem. So for that, what is the information? You do the clustering. This is a point, do the clustering and do the L fitting. So this is L, W, and this is theta. Those are the measurement. So your measurement is going to be X corner, Y corner, length, width, theta. Are you okay with that? The measurement is this. After clustering, what do you think this is? Radar or LiDAR give R and theta. First we convert this into X and Y. Then we do clustering. Okay? After clustering, we get X corner. So you do the clustering, L fitting, then that gives you X corner, Y corner. That's the next one. L with theta. That is that. Okay? So you can consider this as the pre-processing step. This is a pre-processing step. After that, we are going to use a normal nearest neighbor EMK. Are you okay with that? We are going to do that, but in the nearest CMK, we have a way to identify corner swap. And fix. Okay? But it looks simpler, like if I go deeper and deeper, there are so many. Okay? Let's say let's discuss about one, right? In this one, what is the R of this? What is the R of this? What is this? Because if you do the nearest neighbor Kalman filter, then you need to know the covariance of that, right? What is that? How do you find? For XC and YC, that's a little harder, but still you can go with one of the covariance you have over measurement, right? Let's say I fill this part. What is this and what is this? Because length is one measurement, width is one measurement. What is the standard? Because you have to put a standard deviation in order to filter, right? What value would you assign to this? Think about it. There's no definite answer. What is the value you assign for sigma? Okay, give me a few options. You give me which one is better. Which one would you assign? Because radar gives only this. That's all you know. Sigma r and sigma theta. That's all given and point. But you convert that problem to a different problem, then you have to define the sigma L. Right? Now let's consider this. So your car is going here, another vehicle is going in front of it. Usually you expect detection only here, but sometimes you get detection like this. Okay. So in this case, what is the standard deviation of length? So you estimate a rectangular box fitting will give this one. So this is a L measurement that you get. But the actual L is this. Right? What is the sigma L? In this case, sigma L should be large. Is that right? The sigma L should be a larger value. Okay? But if you are like this, you are here, and the other vehicle is here, then the detections are like this, and the box is like this. In this case, sigma L is small, but sigma width is high. Right? So, and if the vehicle is somewhere like this, and if you have points like this, sometimes the rectangular box might be here. It varies, right? So then you may need to set that sigma L adaptively in order to get a better performance. Okay? How do you do adaptively? Because there's no definite answer for this. These are ad hoc things that you have to do in order to make it work. Okay? So usually what I do is I assume the vehicle length, I know the vehicle length, like 2 meter times say 3 meter for example, or 4 meter. Assume that this is not always great because what if you have a truck on the road instead of car? That's a differential like that. But even if you assume it's a cars and vans, and if you know this is a case, and if the meter, the length says 1.5, then we can say sigma L is large, or assign a larger value. Right? So you do that. Okay? Once you do that, you estimate the length. Okay, now let's talk about switching the corner. We talked about switching the corner. Your corner is here. Okay? Before in the prediction part, you want to switch to here. But how do you switch? You subtract the L and theta, right? So if you subtract L, say it comes here. Is that correct? That's not covering the actual corner. So you have to use this sigma L also in that. So what do you do? So that means this has to be like this. Okay, so when originally it was small, originally the estimate of the corner was small. But now we are trying to switch that corner to this point. But we have an error in the length. Because of that, our estimate becomes bad. Because it's switching, we don't know exact length. So when you switch, you introduce more uncertainty to it. Okay? So similar to that, there are several small factors that you have to consider when you make it work for real system, especially for this self-driving vehicle. So that is why if you look at the video I had, you would see that, right? Say this and that. See? These are cars, but the shape doesn't look car because when the vehicle is far away, you won't see the whole object. So you will see if you go. These seems okay, but okay, let's focus on this and see whether the corner switches. Okay. It won't happen. Okay, maybe look at this one. This one is coming here. Hopefully, that's corner will switch for that. Did you see that? The corner suddenly jumped from this corner to that corner. that we have to do it ourselves. And the other one is, that is easier. That is easier. But sometimes if you see that the vehicle in front of us, this corner is switching between this and that. That is little complicated. Like if you see that. So look at the vehicle. One. So you see that corner is switching here and there. Because that can be closed. Depending on whichever is closed, right? So that is a little harder problem. That also you have to switch. Based on the way you have to switch. Yes, I believe so. Because usually it's mounted somewhere, then these are ground, right? These are ground, right?
Immediately after that, there is.
Yeah, this area is not there, right? The reason is that I believe so they have, I am not a good artist. So basically what they have is if the car is our car is like this, the car is like this, they mount the LiDAR on the top of the middle. So if you have it in the middle, so when you go down, so because some of the car part will block some area. So when you go here, so if you go here, so some of the region won't be visible from there. So that is the reason to have the blindfold, nothing else, I will, in my opinion, right? So the LiDAR is here, so it's going, and this is where you can see that. Okay. What are the additional challenges we have here? But this is LiDAR, right? So LiDAR, you have more dense cluster, the sleeping is here. When it goes to radar, we have some additional challenges because we won't have this many detection. Then even the orientation will fluctuate here and there, shape will fluctuate and so on. Okay, with that I can stop, and that's all I wanted to teach. I think we covered everything. But if you have any questions, we can discuss a short question before we start the quiz. Any general question, anything on based on what we studied? But I would recommend, based on my observation, you guys are good with the theory, but when it comes to implementations, most of you struggle. That's what I found in the lab, right? So maybe you may need to practice a lot on the coding side yourself. That is important, right? So eventually, like 20 years maybe before that, the researchers is different from the who developed the code. I don't know if you know Barcelona, who's an expert on typing, right? He never writes a code. That's fine. But this era is different, right? There's no separate program. At least you have to write a code in MATLAB, somebody will convert to C or C+. But we have to write. Everybody has to write that. So that is important. And also, like, if you don't write the code, like even if you develop algorithm, give it to somebody, you are not sure whether they implement properly. That's why you want to develop and test it on your MATLAB and give it to somebody so that even if they develop in a different language, they have to make sure that the results are identical, right? That's their job, right? But you have to develop. That is one reason. Other reason is that when we write papers, usually we get ideas by implementing, right? So first we write the algorithm, then implement, run, find out issue, go back to the theory and fix it, right? So implementation is important, right? But always we make mistakes, then you have to have good debugging skill and so. But coding comes with practice. That's all I can say, right? Okay, then get ready for quiz, and then I'll be here. Like I'm leaving only after 2 o'clock from here, at least, so we can just check if you have any.
The quiz will be in block 3. Will take tutorials. First.
So we have